Multivariable Calculus, Section 12.6, Linear Approximations, using the tangent line to approximate points on the actual curve. Linear approximations for single variable calculus. We have a curve with 2 points, and we have a tangent line. And the difference between the two y values is delta f. Along the tangent line, the distance vertically is called df. And if the curve is concave up, df will be a little bit smaller than delta f. If the curve were concave down, df would be a little larger than delta f. Notice also that dx and delta x are equivalent. So if we subtract the two y values, we get delta f, which can be approximated with df, or otherwise in Leibniz notation it would be delta y and dy. Now notice that we can write the derivative two ways. Df divided by dx equals f prime of x, and so if we multiply both sides by dx, we get df, or the approximate change in y, to be the derivative times dx, or if you prefer, times delta x. Since delta x and dx are equivalent, they're interchangeable. So we have the function value at x plus delta x approximated by the old function value at x plus the change along the tangent line. And so we can rewrite df as f prime delta x or f prime of x dx. Linear approximations for f of two variables. The actual change in the function is the difference between the new point when you add changes in x and y minus the old point. So in other words, the change in z is the new z value minus the old z value. Now in single variable calculus, remember on the last slide we said the change, the approximate change of f was the derivative times the change in x, or the derivative times dx. So if only x is changed, then if we take the new point minus the old point, it can be approximated by the partial derivative with respect to x times dx. And if we only change y, then the difference between the new point and the old point can be approximated by the partial derivative with respect to y times dy. So if we add those two together, then we get an approximation for the actual change in the function if both x and y are changed. And we can approximate the new point by adding df to the old point. Therefore, the new point is equal to the old point plus the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. In Leibniz notation, the change in z can be approximated by dz, which again is the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. Functions of three variables. If we use w for the name of the function, then in Leibniz notation we get the partial derivative of w with respect to x dx plus the partial derivative of w with respect to y times dy plus the partial derivative of w with respect to z times dz. And there it is in Newton's notation. Same formula, different notation. Now if we have more than three variables, as you can tell, these formulas tend to get rather cumbersome. And so I'm going to introduce some new notation that we won't really use in this section, but it is introduced in this section. We'll need it later. And that notation involves the idea of gradient vectors. So let's start with a vector x that is multidimensional. It's in n space. In other words, in mathematics, we're not confined to 1, 2, 3, or 4 dimensions. We can have as many dimensions as we want. So let's say we have n dimensions. Then define the gradient vector of f of x, the vector x, to be with an upside down triangle. The gradient vector of vector x is the vector whose components are the partial derivatives with respect to x1, x2, x3, and so on. For example, in 3 space, when you have a function of two variables, then the gradient vector is the partial derivative with respect to x, comma, partial derivative with respect to y, or in Leibniz notation, partial derivative of z with respect to x, comma, partial derivative of z with respect to y. And in 4 dimensions when we have a function of 3 variables, then the gradient vector has 3 components written that way. Now, if we have another vector, h, equal to the changes in the various independent variables, x1 through xn, then if we dot the gradient vector with vector h, the increments in the variables, then we get the total change in this vector valued function. So now we have the function of vector x plus vector h approximated by the function of vector x plus the gradient vector dotted with the h vector. And that's a lot more compact than having a whole list of n terms that we're adding together. Number 2, compute the differential dw for w equal to e to the negative x squared minus y squared. Well, recall our handy-dandy formula for dw. So dw is the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy plus the partial derivative with respect to z. And there is no z, so maybe there wasn't one in the first place. Maybe they just used w instead of z. Or if there is one, then its partial derivative is 0. So notice that the partial derivatives with respect to x and y are almost identical, except that the derivative of the exponent, if you consider y as a constant, then the partial derivative with respect to x is negative 2x. And if you consider x squared to be a constant, then the partial derivative using the chain rule becomes negative 2y. So let's clean that up a little bit. Factor out the negative 2e to the negative x squared minus y squared. And there you have your answer. Number 6, compute the differential dw for w equal xz squared minus yx squared plus zy squared. So again, we are using the formula above. We have the derivative, the partial derivative with respect to x times dx, and the partial derivative with respect to y times dy, and the partial derivative with respect to z times dz. Notice that in the first partial derivative, the last term did not have an x in it, and so it went to 0. And in the second one, the first term didn't have a y in it, so it went to 0. And in the last one, the middle term didn't have a z in it, so it went to 0. And hopefully the rest is clear. So then we clean that up just a teeny bit, and there's your answer. Number 14, compute the differential dw for w equal s plus t over s minus t. Now this is kind of weird. They're using a w, but then they're using s and t, and there's only 2 independent variables, so we don't really need to worry about a third one, even though they're using a w. You can use any letters you want, and this book loves to use a variety. So we need the partial derivative with respect to s times ds, and the partial derivative with respect to t times dt. Notice that we're using the quotient rule, and that the derivative of the numerator is 1 for both s and t, but the derivative of the denominator is 1 if you're looking at the s term, and negative 1 over here on the right if you're looking at the t term. Now a lot of things cancel, which is happy, happy, happy. And so if we clean that up, we get this as our differential. Now the book rewrites that with 1 denominator, so if you prefer, you can rewrite it that way. Number 20, given the function of 3 variables x, y, and z as follows, and point P, which is a nice point, and Q, which is not a very nice point, use the differential df to approximate f of Q. Now, we could get the exact value, or very close to the exact value, by using our calculator and just plugging the numbers for point Q into the square root of x, y, z. But you have to think about Newton, who did not have a handy-dandy calculator and could not do that. He had candlelight, he had a quill pen, but he did not have a calculator. So this whole idea of approximations it's the idea that's important. Nowadays we don't really need it to do the calculations, but you would need it in a general case or to prove something, etc., etc. So we'll go ahead and approximate f of Q with f of P plus the differential. Here's the formula for the differential, And notice that the changes in x, if we're going from the nice point to the not so nice point, both x and y go down by 0.1 and z goes up by 0.1. So now we need the derivative with respect to x dx plus the derivative with respect to y dy plus the derivative with respect to z dz, and you already know how to do this, so I'm not going to belabor it. And then we plug in the numbers that we have for x, y, and z using the nice point, and also using delta x, delta y, and delta z for dx, dy, and dz, and we get an approximate change of negative 0.15. So now we're going to approximate the function value at point Q with the function value at point P, which is nice, square root of 1 times 3 times 3, minus or plus the differential, or minus 0.15, and we get 2.85 for our approximation. Now if you'll compare that to the calculator value, it's not too bad. Not a great approximation, but good enough for Newton. Number 24. Given f of x, y equals this quantity and a nice point and a not so nice point, use the differential to approximate f of the not so nice point. Well, our change in x is 0.1 because x goes from 1 to 1.1, and our change in y is negative 0.1 because y goes from 0.5 to 0.4. Here's our formula for the differential. So the partial derivative with respect to x using the product rule, and notice that the derivative of x minus y is just 1 if you're treating y as a constant. And notice that in the second term we have a composite function, so we take the derivative of cosine, which is negative sine, and then the derivative of the inside, if y is treated as a constant, is 2 pi y. Then we plug in the numbers from our nice point, and we get our f sub x to equal negative 1. Here's the partial derivative with respect to y. Notice that this time the derivative of x minus y is negative 1, and the derivative of 2 pi xy is 2 pi x. Again, we plug in our values, and we get 1 for that value. So that means that df is f sub x times delta x plus f sub y times delta y, and that comes out to negative 0.2. So now we can approximate f of q as f of p plus negative 0.2, and so if you plug in 1 and 0.5 into the function, you get a nice value of negative 0.5. So we have negative 0.5 minus 0.2, which is negative 0.7. Now if we take out our handy dandy calculator and plug into the function, we get actually a better approximation from the calculator, and this time our linear approximation using calculus is not very good. Number 28. Use differentials to approximate this quantity. Well, now remember that Newton didn't have a calculator. I never had a calculator. So we're going to let our function have two variables, two independent variables, x and y. And so our function is the cube root of x divided by the fifth root of y. And our nice point has to be near 25 and 30, but come out nicely for our friend Newton. So we're going to use a nice point of 27 and 32, both numbers near 25 and 30. So here's our function written in a way that's easier to take the derivative of. And so our partial derivative with respect to x is as follows, and then we plug in our nice numbers for x and y, 27 and 32. And then our partial derivative with respect to y is just a little bit different, and then we plug the numbers in again and get that for our value. So now let's take a look at some other values we're going to need. The change in x is negative 2, the change in y is negative 2, because our not so nice point has values that are less than our nice point. And if we plug 27 and 32 into our original function, we get 3/2. So the differential is equal to the partial derivative with respect to x dx plus the partial derivative with respect to y dy. Plugging in the values we've already computed, we get negative 79 over 4320. So now we can approximate the not so nice point by adding that differential to the value for the nice point, and we get an approximation of 1.48 blah 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 blah. Okay, so now we take out our calculator and plug our not so nice values into the function, and this time you'll see that we got a pretty good approximation. So now it's your turn to work some problems in this section. Have fun.